Hello, Pol 251 students. We're going to be talking about cross-tabulation and cross-tabular comparisons. So when we're making comparisons between independent and dependent variables, our kind of overall logic here, especially when we talked about hypothesis testing, was that cases that differ on an independent variable should also differ on the dependent variable in a hypothesized way. So if you think about, say moving from males to females, what does that do to vote choice? If you move from Republican to Democrat, what does that do to, say, support for gun control? If you move from high school to college education, what does that do for, say, income overall? So that was our overall logic of hypothesis testing. And then from a statistical standpoint, what we're trying to figure out is when we see independent relationships between independent and dependent variables, the question is if this is real or if it occurred by chance. So so this is where we were talking about having alphas of 0.05, generating confidence intervals, figuring out if observed values fall within a predicted range or outside of a predicted range. And that's where we've gone so far in the past few weeks. Most recently, when we talked about these relationships between independent and dependent variables, we talked about it in terms of comparison of means. So we had a mean of a dependent variable and looked to see if that could vary across values of independent variables. Now, we didn't do that explicitly because I didn't show you guys two sample t-tests, but you did create confidence intervals around the mean level of a variable. And as you may have noticed, these were interval and ratio level variables. So for instance, in the exercise on making confidence intervals, we had a variable for SAT scores. Well, this is an interval level variable. It has units that are ranked in an order, and the distance between each of those units is the same at all times. I also had another question in the exercise about height of males. That's a ratio level variable. It has a meaningful 0, where 0 means no height at all. And then for each 1 unit increase, it's always the same. One unit is 1 inch across the board. And we created these confidence intervals, and I had you compare whether certain values were similar or different to this mean of a population or mean of this sample. So we've already done this kind of hypothesis testing and these kind of comparisons looking at means. What we're going to be talking about here is looking at these kinds of comparisons using cross-tabulation. So when we talk about cross-tabulation, we're going to show the distribution, usually either in raw numbers or in percentages, of cases across values of an independent and a dependent variable. One thing that's important to note here is that cross-tabulations are about making comparisons between nominal or ordinal variables. So things like calculating a mean doesn't really make sense when you have a nominal variable like categories of race or categories of gender. Doesn't also really make sense when you have ordinal variables, again, say different categories in a Likert scale. So when we have these kinds of cross-tabular comparisons, it's about figuring out relationships between two nominal and ordinal variables. And they're called cross-tabular comparisons or cross-tabulation because we create a table and we have one variable that represents our rows and another variable that represents our columns. So the actual independent and dependent variables are organized in a table. And then once you set up this table of comparisons, you can then ask, is the classification of one nominal variable related to the classification on a second nominal variable? So for instance, say you have vote choice. This could be between voting yes versus voting no on a local state referendum. So that's nominal. It's either yes or no. There's just categorizing answers. And then you could say, well, is there a difference in that nominal vote choice between men and women? Well, again, gender is also a nominal variable. It's simply categorizing units. There's no ranking or ordering to them. So you can basically look to see, well, do men and women differ on vote choice of a particular referendum? Or say you look at something like Trump approval. Again, this can be nominal. If you look at Gallup polls, it's usually a dichotomous choice. You're either approving of Trump or disapproving of Trump. And then you could ask, like, well, does that breakdown of approval versus disapproval, how does that breakdown differ between whites, African Americans, Latinos? Where here you have race as a nominal variable with different categories for different ethnic backgrounds. So those are some clear examples where we could see cross-tabulation comparisons. And as we'll see in the next video, we can then use the chi-square statistic to make inferences about those relationships, to make an inference to see if the relationship between these two nominal and ordinal variables are actually statistically significant. So I want to talk about comparing proportions in two different ways with two different examples. First, imagine a researcher is asking if there's a relationship between having health insurance and supporting healthcare laws. And this was a large debate going on as the Affordable Care Act rolled out. So is it possible that people who already had health insurance were less likely to support the ACA than people who did not currently have health insurance? Maybe those without health insurance had something more to be gained from the policy. So I have some Gallup data that was collected in 2013, and I've kind of zoomed in on the portion of this data that's most appropriate for our purposes. So here we have views of healthcare law, and each of these rows represents either approving or disapproving. So by healthcare law, we're referring to the Affordable Care Act or any other new healthcare law proposed by Congress. And again, this approved, disapproved, this is a nominal variable. It just simply categorizes two options of opinions that people have. There's no real ranking to this. So we have disapprove and approve. And in our data here, we have 42% of people said they approve of the law, 53% disapprove of the law. We then here have this other category or this other variable asking, do you have health insurance? And again, this is also a nominal variable because it either says, yes, you have health insurance, or no, you do not. Again, simply categorizing whether or not people have health insurance, no ranking, no order to it. Now here we see four different percentages. We have the percentage of people who approve that do have health insurance and the percentage of people who approve that do not have health insurance. So basically the difference here between 40 and 49 is 9%. So among people who approve of the healthcare law, more of them do not have health insurance. Let's look at this row here for disapprove. Here we see that 55% of people who disapprove of the healthcare law do have insurance, whereas only 46% of the people disapproving of the healthcare law do not have insurance. Again, a 9-point difference. Now, this is your cross-tabulation setup. It shows in each cell a percentage of respondents. So we have people who approve or disapprove healthcare. We have 40% of those that have insurance, 49 who don't. Of the disapprovals, 55 have insurance, 46 don't. That is your basic setup of a cross-tabulation. That way we can visualize the relationship between these two nominal variables, and we can look and see patterns whether people who do or do not have health insurance have different opinions of the healthcare law. Here's another example, and this is taken from the 2018 midterm elections. So imagine a researcher has a question asking about the relationship between age and how people voted for their House candidate of choice, so the House of Representatives vote choice. And here we see each row represents a different category of age. So people 18 to 29 years old, 30 to 39 years old, 40 to 49, 50 to 64, and 65. This is an ordinal variable. Its categories are ranked such that higher values mean older in age. However, the distance between these units or these categories are uneven. 18 to 29, that represents a larger age range than 30 to 39, which is also a different age range than this 50 to 64 or this 65 plus. So each 1 unit increase between these 5 categories isn't the same as, say, 1 year or 10 years or 20 years. It also, it varies. Then what we see in our bars here, based on these different colors, is who someone voted for. And here we have 4 options: the Democratic candidate, the Republican candidate, not sure, and other. These are also nominal variables. They're simply just categories asking how someone voted. There's no rank or ordering to it. The fact that Democrat is listed above Republican has no numeric actual real value to it. It's just 4 different categories of possible things people could have chosen for their House of Representatives vote. And here we see percentage. So we see of people 18 to 29, 54% of them voted for the Democrat, 26% of them voted for the Republican. In contrast, as we go down to our oldest age category, 65 plus, we see 42% of those people voted for the Democrat, whereas 49% of them voted for the Republican. So here, again, at a glance, by doing this kind of cross-tabulation, we can visualize and see that it looks like as people get older, they tend to vote less for the Democrat, and as they get older, they tend to vote more for the Republican. So just simply at a glance, if I was a researcher saying, is there a relationship between age and who someone votes for in the House of Representatives race in 2018, I would say yes, there is, at least visually at a glance, without a statistical test. Just sort of your general intuitive take on it. You see this cross-tabulation, you see that the proportions of people voting for the Democrat decrease with the older you are, the proportions for Republican increase the older you are. Now, with those 2 examples, I was simply eyeballing numbers. There was no statistical test, there was no calculation of alpha or any kind of confidence interval or any kind of uncertainty baked in. So in order to actually figure out if there are relationships between those nominal and ordinal variables, what's going to have to happen is something known as a chi-square test. And the logic behind a chi-square test is the following. First, we work from the premise of a null hypothesis, where there is no difference in the dependent variable between groups in the population. So if we are observing any differences, it's just chance variation in the sample. So for instance, in the case of healthcare attitudes, there should be no difference in approval versus disapproval based upon someone who does or doesn't have health insurance. If we see any variation, it's because of random chance or random error. Same with that graph we just saw about vote choice in the 2018 midterms. If the null is true, if there is no difference in the dependent variable between groups, then the proportion of Democratic and Republican voters should be the same across all age groups. That, say, 18 to 29-year-olds should have the same rate of voting Republican and Democrat as those who were 65 plus. So that's the premise of the null hypothesis, that there shouldn't be any differences in your dependent variable across groups of the nominal variable. Essentially, you have a chi-square of 0 plus some random error. And the way to figure this out, the way to figure out whether we can reject the null hypothesis or not, is to compare the values we actually observe, and these are going to be notated F sub O, where O means observed, and we're going to compare the values or the proportions we actually observe to those that would expect if the null is true, or those we would expect only if differences are occurring due to chance. And these values would be written out F sub E, where E represents expected. And so that's where we're going next. In our next video, I'm going to walk you through an entire example of how to do this kind of cross-tabulation chi-square hypothesis testing.